Great. I will just check if the mic is on. Yeah, it should be on. So yeah, great. So many of you made it here today to the AI paper spotlights. We have recently changed our name. So we were the paper reading group up until very recently. And well, you don't really need to read papers to come here. So we thought it would be nice to change the name to AI Paper Spotlights, because this event is about the latest research trends in machine learning and artificial intelligence. And we usually have one or more speakers here come and speak about their research or other people's work in this event. And yeah, so just a few words about the company that I work at. My company is called Merantix Momentum. So it's one of the sub-ventures of Merantix, and we both run a machine learning consultancy and also a machine learning research unit. And we're basically making the magic work and letting these two teams inspire each other. Yeah. So this is, I think, all I'm going to say about myself. Today, it's my pleasure to introduce Verena Weber. She has a background in statistics from the Humboldt University of Berlin and has worked at Amazon for the last three and a half years or so in the natural language processing unit. And she will give insights about her recent publication that has come out of her Amazon lab, and will, I guess, yeah, speak a little bit towards the ins and outs of it, and also why it is relevant and necessary. And yeah, without further ado, I think I would like to let Verena take over. Just one more thing, this time we're doing the questions at the end, so you'll have plenty of time to ask all the questions that you might want to ask at the end, and I will pass you the microphone such that the online crowd can also hear us. And if the online crowd has any questions or concerns, then I will monitor that in the chat as well, and will forward some of the questions, or all of them, if there are not many, at the end. So thank you so much. And Verena, please take it away.
Yes, thank you, Alex, for the great introduction. Hello and welcome to everyone here at the campus, but also online. Really happy to see so many faces here. Glad you made it here today. Yeah, my name is Verena, and I have the pleasure of introducing my research today, and the topic will be regression-free model updates in spoken language understanding. And don't worry, I mean, if you can't make sense of this right now, we will get there. But before we start, I would like to emphasize that, of course, I haven't done all this work alone, but this was a collaboration with my colleagues from Amazon, specifically Andrea, Alessandro, Tobias, and Davide. So also thanks to them for this great collaboration. We actually published this work at the ACL this year. So if you want to learn more about the topic, feel free to also have a look at the paper afterwards. All right, so what is on tonight's agenda? So first of all, I'm gonna introduce myself a little bit. I mean, Alex already said a few words, so I'm not gonna bore you too much with that. Yeah, after that, I'm gonna give you a little bit of context. So basically explaining in what kind of context and what kind of motivations we had to work on this approach. And then I'm gonna introduce the core idea of the paper. After that, I'm gonna walk you through the experiments and results. And then in the end, we will have time for questions and a discussion. All right, so quick intro. Yeah, again, my name is Verena. I'm gonna start working as a freelance machine learning scientist probably in September. So in case you need someone with NLP expertise, let me know. Until recently, I was a research scientist at Alexa AI Amazon. And so my team was focused on natural language understanding there for German and French. And before joining Amazon, I gained some data science experience across different industries and companies. But yeah, I'm not going to bore you with the details. If you want to know more, just connect with me on LinkedIn. I have more details there. And to make this a little bit more interesting, I thought I'd include a little bit of a fun fact. So actually, during my studies, I lived in China for 2 years, where I studied Chinese. But I also discovered my interest for Eastern philosophy and religions. So in case you speak Chinese, you can try me. I mean, it's fading away, but a little bit is still there. All right, so let's get started. Natural language understanding, or NLU. Let me give you a little bit of context. So as I said, this work was done during my time at Amazon, where I worked for Alexa. And Alexa now still works in a pipeline approach. So that means basically you have several tasks that get executed sequentially. And the first one is just break word detection. And after that, you then have like automatic speech recognition, where audio is simply transcribed into text. And after that, this is where then natural language understanding comes in. So basically, we get as input a text, right? This is not audio or anything like that. So imagine you have this example, a user says play Imagine by John Lennon, then the NLU model basically has the task to extract 3 pieces of information. The first one is domain. So basically just saying a rough domain that this request goes into. So in this case, it would be music, but it could also be weather or home automation, just a very rough classification. Within each domain, you then have a set of several intents. And the next step is to then classify what specifically that user wants within that domain. So for this example, it would just be play music. And then last but not least, you need to kind of get the details extracted that you need to fulfill this request by downstream services. So it's a bit similar to extracting named entities. So NER stands for named entity recognition. And basically what we do here is just we have one label for each token in the sequence. So in this example, you would label Imagine as song name, and then John and Lennon, the 2 tokens, would both get the label artist name. Play and buy would just be labeled as other, because we don't need these 2 words. This information is already included in the domain and in the intent. Now, how does this model work? So basically, with each utterance, we take a 2-step encoding approach. So whenever the request comes in, we first encode the utterance with character, positional, and potentially catalog embedding. So catalog embedding is only used for IC and NER. We don't use this for domain classification. That's why it is in brackets here. Character is just normal BPE, what you would know from a normal BERT-based model. The same is the positional embedding is also what you use for a BERT-based or transformer model. And then catalog embedding is a bit specific to NER and IC. So basically for each entity, we have a list of possible entities. So for song name, we have a list of song names. For artist name, we have a list of artist names. And then for each token, you simply check whether this token occurs in any of those catalogs. And then you just record this information and convert this into a vector. And then we basically just concatenate those 3 embeddings and then feed this into a tiny BERT to get a contextual embedding of the utterance. So in the end, we then have like the encoded utterance. And to extract the 3 pieces of information that I showed on the slide before, we pass this encoded utterance into 3 different decoders. So for domain classification and intent classification, we simply use pooling and then max entropy classifier. So this is just a normal classification task where you get 1 label. For NER, it's a little bit different because we want 1 label per token. So it's a sequence labeling task. And basically, you have 2 options there. You could just treat each token independently, right? And run a max entropy classification for each token in the sequence, which can be done, but is not ideal because you don't take the correlations between the labels into account. So with the CRF, which stands for conditional random field, you can also model these correlations or transition probabilities between labels. And this is, the state of the art also for NER. So keep that in mind, we will use that later. Now, let me explain what regressions are and what role they play for customer experience. So at Amazon, we have this principle that we don't do research just to do research. So research needs to be customer focused, which means it either has to solve a customer problem or it has to enhance customer experience. And regressions are a problem for customer experience. So we update the NLU model on a regular basis. And ideally, this is not something that the customer would notice, or unless, only in a positive way, but never in a negative way. So imagine at time t, the user again has this request, play Imagine by John Lennon, and then the request goes into NLU model at time t, everything works fine. But then maybe a few weeks later, they try again and the request goes into model t+1. So we updated the model in the meantime, and all of a sudden this request doesn't work anymore. This is of course very frustrating for the customer. And also for us scientists, it is important to make sure that all the utterances or the requests that are frequently used work well. And we, as scientists, do not have a lot of control over these regressions, especially because it could very well be that maybe the overall accuracy even gets better, but you do have a regression on high frequency utterances. And this is, of course, something we want to avoid. And at the moment, actually, this is, before using this approach, a lot of manual effort was used to make sure that high frequency utterances are not affected. And to kind of, make this a bit more efficient and reduce manual effort where possible, we were trying to think about, okay, how can we get better control over these regressions already during model training and not after the model is trained and tested? So we started looking a little bit into the literature and then actually also found a paper that came out of Amazon AWS. And the core idea of this paper, or the main proposition, is actually positive congruent training. The paper is called Positive Congruent Training Towards Regression-Free Model Updates from Jens Sudje and others. And we basically build on this approach. So what they do is basically they take a data set and then they divide it into 4 subcategories, and they by comparing the 2 model predictions. So assume you have an old and a new model, right? Then you can divide this into 4 categories where both predictions are correct. So that's of course fine. You don't really care about that subset. Then you have this subset where both models are wrong. This is also not really a problem because the old model usually already was in production, and we kind of know that there is no major issue, and it's maybe just minor errors, which are fine to some extent. So we also don't really need to worry about those. Then, of course, you have what they call positive flips, where the old model is incorrect, but the new model gives you the right prediction. I mean, this is great, so also not something you need to worry about. But what you want to address is this negative flips, or what we call regressions, where the previous model was right, but the new model is wrong, because this can lead to serious problems. And they propose a modified loss function, and try out several approaches. And to compare these different training modalities, they suggest this negative flip rate metric. So basically what they do is they just count the number of negative flips on a data set and divide it by the size of the data set. So, and this is also the metric that we then later on use to compare training approaches. Yeah, now let's actually get to the core of this and have a look at the loss function. I'm gonna have a couple of equations here on the next few slides, but I'm gonna walk you through it, so bear with me. Yeah, so we start with this one at the top. This is the positive congruent training loss. So this is what they call it in the paper. We later on refer to simply focal distillation, because this is the basic approach that underlies this method. And you can see it is made out of two components. So the first part is just the normal cross entropy loss. So this is the standard loss function that you would use for a standard classification task. And then what they do is they add another term with a trade-off parameter lambda. And this term is based on focal distillation, and it looks at the differences of the output probability distributions of the two models. So the conditional probability of y given x. So this is what we estimate with each model. Now, if we make this term a little bit more concrete, so basically this is again composed of two things. First, we have this filtering function f of x and y, and then we have a distance measure that quantifies the difference between the probability output distributions of the old and the new model. And what this filtering function does is basically it scales this distance by a factor, alpha, and then depending on whether the old model gave the right prediction, it scales it by alpha plus beta. So basically this factor depends. So we put more emphasis on training examples that were correctly interpreted by the previous model. So it's important to mention that here we run the old model on the training data that we now want to use for the updated model, right? Because we want to understand where the old model is already able to give a correct prediction. Yeah, so one thing that's still missing is now this distance measure here. In the paper, they experiment with different measures. One is Kullback-Leibler divergence, so that's a standard way of measuring the difference between two probability distributions. And the other one is what they call logit matching. Since logic matching performed better, we just go with that and we don't experiment with anything else. So logit matching is also actually quite straightforward. So what you do is you simply take the mean squared error of the pre-softmat logic between the old and the new model. So basically the logit is is what, so you put the logit into the softmax, and then this gives you the probability distribution. So if you compare the logits already before that, this is a good indication of how different your probability distribution is after the softmax. Right, okay, so this was the paper that we found, and this was the approach that we built on. Now, what did we do and how did we extend this? So like I said, we were trying to solve this problem of controlling regressions in our NLU model. So we thought about how can we use this work from the image classification realm in our NLU model. And maybe you remember that DC and IC, so domain and intent classification, are simple classification tasks. So this is quite straightforward to transfer from image to text. For NER, it was a little bit more tricky because we don't just have a simple classification task, but we have this sequence labeling task where we want a label for each token in the sequence, and where we also model the correlations between the labels. So ideally, what you want to do is distillation on a sequence level. We looked into that, and we also found a way to do that, but that was quite computationally expensive. So in the end, we decided to try out an easier way and simply treat the distillation as a token level problem. So treating it as a token level distillation, we come up with this focal distillation loss here. So basically, we just take the sum of the focal distillation loss over all the tokens in the sequence. So if you look at this equation here, you can see that here we just take the sum over the length of the sequence. And now we have the probability distribution per token over all the classes, which are the token labels. So we just treat each token as a simple classification task. We also experimented with an extension of this approach. So usually data is noisy, and I mean, this focal distillation relies on labels to understand if a prediction is correct or not. Now, if the label is wrong and the model gives the wrong prediction, then focal distillation would bias it towards a wrong label. So we wanted to understand if maybe there is a way to put to also incorporate this label noise and maybe put less weight on instances that might have a noisy label. For that, we added this noise-aware weight into the focal distillation loss. So this part here over here is just what we saw previously. It's a standard loss. And then what we added is just G of area under margin. And this area under margin is a metric that comes from a paper from Geoff Place and others, identifying mislabeled data using the area under margin ranking. And this G function then simply scales this metric between 0 and 1. So we again have a scaling factor here in the loss. Now, let me explain a little bit what this area under margin is. So it's basically just, you calculate a margin for each epoch in the training process, and then you just take the average of that. Now, what is this margin? Well, it's just the logit of the labeled class, or so basically if the class label is dog, then it's logit of dog minus the logit of the highest logit of the other class. So this sounds a bit complicated, but let me show you a picture, then it's easier to understand. Next. Yeah, okay. So this is also from the original area under margin paper. Here, the plot on the left shows a very easy and correctly labeled example. So you have a dog here labeled as dog. And then the screen line is the dog logit that becomes higher over time as the training progresses, which makes sense because the model learns what a dog is. On the other hand, this highest other logit, whatever that may be, decreases a little bit over time. So you get this margin between the two, this difference. Now, what happens if you have a correctly labeled example that is maybe hard to learn, where the model has a difficult time to learn it? Well, then it just takes a little bit longer. The logits remain closer for some time, but then towards the end of the training, you still have this margin. Now, what happens if you have a bird labeled as a dog? Well, then this other logit, which is now the bird logit, actually remains quite high because the model towards the end of the training kind of knows what a bird is. So it still thinks it's a bird. And you don't get this margin because, I mean, it starts to memorize maybe this dog thing, but you don't get this margin anymore. And this is basically what the area under margin uses.
May I ask a question? Isn't that a matter of time that this margin will flip at one point? On the last example.
What do you mean by flip? That the green one goes up and
exactly that's one.
But then you would probably start overfitting the model. Okay, so what are our research questions and what are the experiments that we ran to answer those? So basically, we ask ourselves 4 questions that we wanted to answer then with the experiments that we ran. So first of all, we just wanted to show that focal distillation in our application or use case can actually reduce negative flips, as was shown for image classification. We also wanted to understand if this a little bit simplified version of using focal distillation for NER, so with this token level distillation, which is a simplification, if that works well enough to also reduce negative flips. The third question came out of some discussions because we were wondering if maybe focal distillation might restrict the model's ability to learn something new. Because what focal distillation does is that it biases the new model towards the distribution of the old. So we thought, okay, maybe if we add more features, that this might become difficult. And of course, we do need our model to learn new features quite often. And then last, we wanted to understand if this idea with using this area under margin in the loss can help to mitigate the effect of potentially noisy labels. Yeah, we mostly consider the data update scenario here. So that means, so when we update the model, the only thing that changes is the training data. We keep the architecture, the hyperparameters, the label space fixed. So because that is also most of the time the scenario that we deal with. Only, of course, for this third question, where we want to understand the impact on learning capacity, we update the label space for the model. So we add a new label in the training data. Yeah, we then run experiments on open source benchmark, on the open source benchmark SLURP, which is a quite standard benchmark for spoken language understanding. I also added the paper here in case you are interested to try it out. And we also run a lot of experiments, not with the production model, but with bird-based models from Hugging Face to speed up computation time. We do have a couple of experiments on internal data as well as with a production model to kind of also quantify the effect on our internal use cases. And as I mentioned, yeah, usually we consider just the data update scenario, and only for question number 3, we also add a new label to the label space. Yeah, so now I'm just gonna go through all these 4 questions and show the results to answer those. So we start with the first question to see if focal distillation is effective for domain and intent classification. So we compare focal distillation with the baseline, which in this case is just normal cross-entropy training. And we look at accuracy and negative flip rate on the SLURP data set here. So you can see that there is almost no change in accuracy, but at the same time, we are really able to reduce this negative flip rate for a domain classification by about 28%, and for intent classification by about 34%, which is quite significant. So these are the results on the internal data. We can only report relative numbers here, no absolute numbers. That's why this table is a little bit emptier, in case you were wondering. Again, we see that the accuracy doesn't change that much, but at the same time, we're able to reduce negative flip rate. And again, quite significantly here. For English. We did experiments for English and German. However, I have to say it's not quite comparable. So the numbers are not really comparable, because for English, we actually did change the training data. Whereas for German, we wanted to kind of just see the fact what happens if we retrain on the same data. Because even if you retrain on the same data, due to the randomness in the training process, you still get negative flips, and we wanted to isolate this effect. So that is why the numbers are quite different here, or the magnitude of the reduction in the negative flip rate is quite different here. All right, so let's move on to the second research question about named entity recognition. Again, we start with the results on the public data set. And also here we see that there is not a lot of change in accuracy, but at the same time, we can reduce negative flip rate by 8%, which is not as much as we could for the DC and IC task, but still quite significant and still worth it. And the good thing is also, even though we use this kind of simplification of using total level distillation, the negative flip rate is already reduced. Yeah, these are the results on the internal data set. We experimented here with intent classification within 3 different domains. Again, accuracy doesn't change much, so that is good. And at the same time, we are able to reduce negative flip rate. It's not, so the magnitude of the reduction is not the same for all domains. So we think the reason might be that the intent classification models have different levels of accuracy. So basically, if the old model and the new model both have very high accuracy already, there's not a lot of negative flips that you can reduce. And intent classification works differently, or does not work well, or it's not the same level of accuracy for all the domains. So that's how we explain these differences here. Now, does focal distillation restrict the model's learning capacity? To understand that, we simulated 5 consecutive updates, where in each update we changed the training data, and starting from the first, we added a new label into the label space. So this is for domain classification. So we added a new domain basically in the first update. And on the left plot here, you can see the overall accuracy. And I mean, orange is focal distillation, so our new approach, and then baseline is just normal cross entropy. And you can see over those 5 iterations, the curves are pretty close to each other, which is also what we, which makes sense given that we saw the impact on accuracy is not that much, and it's overall accuracy. And at the same time, negative flip rate, which is displayed on this second plot here, is significantly lower for focal distillation and even becomes a little bit lower as you move towards further updates. Yeah, we then also wanted to look at the accuracy on the new label, so the one that was added, because this is where we had our concerns that maybe the model would not learn it that well. And you can see here in the plot that in the beginning, there's a little bit of a gap, right? So after the first update, the focal distillation is below the baseline, but then this gap gets closed pretty fast. And after the 5 updates, they're both on the same level. At the same time, again, the negative flip rate, however, is lower for focal distillation. Yeah, what about the noisy labels? So to understand if this idea of using area under margin in the focal distillation, we simulated different levels of artificial noise in the data set. So we just added some noise randomly to certain labels. And then we compare the baseline focal distillation plus area under margin. For DC, this works quite well for the 20% noise level. However, for IC, it doesn't really work, or at least the results are not very conclusive, because then for the 40% level, this seems to work. Whereas for the DC on 40%, actually FD alone performs better. However, FD and area under margin is still okay. So the results are not quite conclusive here. We think that, maybe there's also a better way of adding this area under margin into the loss. I mean, this was just a first guess, so to say. Also, this is the public data, and it can be that for some intents, there's not a lot of data, but a lot of labels. So the data to label space ratio is not that great, which could impact the performance of area under margin. Here are the results for the internal data, and on the 20% noise level, so just adding noise to 20% of the training instances, it works quite well. However, then if you add 40%, it doesn't seem to work that well anymore. So again, also here, maybe the more noise you have, also area under margin might struggle, and also the impact might be bigger. So here we conclude that there is still some room for improvement, and we could, we would still have to investigate a bit further why we see that on the 40% noise level, this doesn't work anymore. Yeah, this brings me to the conclusion. We basically answered these 4 questions, and let me give you a brief summary of what we talked about today. So we saw that focal distillation works pretty well to reduce the negative flip rates for the simple DC and IC class task. And this was also quite straightforward to transfer from the image recognition application. We also saw that our simplified version of applying it to named entity recognition actually is sufficient to get a significant reduction in NER. So this is also good and worth it. We could also show that there is actually that there's no need to be concerned about learning capacity. So by simulating consecutive updates with focal distillation, we saw that the new model was still able to learn the new label pretty well. And finally, yeah, we saw that FD can cope with noisy labels, but there might still be a little bit of a better way to incorporate this into focal distillation. Yeah, and that is basically all I have for today. Thank you all for your attention and listening. I'm happy to answer your questions. So.
Are there any questions from the audience? Yeah.
First of all, thank you very much. It was very enlightening. I didn't understand how did you do the array under margin because the labels were already noisy and you were relying on the labels still. So was it a subset of the training data?
No, we added artificial noise to the data.
Okay.
So that means you randomly pick 20% of the training data at the 20% noise level, and then you just randomly flip the label. But then if you test, you can still use the original labels. So that's how you can measure the impact on accuracy. Yeah.
Any more questions? I had a question actually. So I saw in the very beginning of your slides that there was like a BERT architecture that was powering the algorithm you proposed, or at least the task that you proposed. Does it also, yeah, this one, does this also, this focal distillation loss, would it also transfer to, for example, to decoder only models like GPT, or is it only suitable for architectures like BERT?
Yeah, I mean, if you have GPT, right, you have a generation problem, right? So, I mean, also what exactly is a negative flip in that case? How would you define that?
I mean, yeah, it's maybe hard to define, but you could like this ask like GPT to predict like a label given some text, and then have compute like similar scores like you proposed, for example. But I'm not sure whether that would actually work.
Yeah, I mean, I think generation is definitely a bit more complex than just classification or sequence labeling. So I don't know if that would be straightforward. Also, yeah, I think I probably would have to think a bit about how to define this negative flip in that case.
Okay. Yeah, one more question.
What is the max sequence of the utterance?
The max sequence length, you mean?
Yeah.
I think 120 or something. Not that long. I mean, usually this traffic is quite short. I mean, of course, you have extreme outliers, which could be more than that, but you truncate at some point.
Okay.
Yeah.
Okay. And what if you have a negation in your utterance? Let's say, I asked Alexa, play Imagine by John Lennon, and then gave a 2 seconds pause and say that, no, play me a Pitbull song.
Yeah, I mean, if there is a pause, it's two different requests, right? It's treated as
two different requests.
Yeah, and then so basically Alexa starts and then stops again. But if it's in one utterance, there is also a label called a negation trigger or something like that. Yeah.
What is the time frame for the pause? Like, let's say, like how it is classified?
I don't know exactly. I mean, that's not something, yeah, that we control.
Thank you.
But it's pretty short. Sometimes, actually, so I mean, I have an Alexa at home, and sometimes if I just think about 1 second, it might already be that I have to start all over again because it's treating it as a separate request. Yeah.
curiosity, the size of the data sets, because I imagine that doing this on a much smaller data sets could throw out your numbers quite significantly.
Yeah, we have a pretty big data set. I can't say the exact number, but it's millions. So yeah. Smaller data sets as well. Yeah, I mean, the public data set that we used is actually not that big. We have the number in the paper. I don't have it from the top of my head, but it's definitely not as big. Yeah. Yeah.
Any more questions? Yes, you have one.
Two questions. So the first one, the principle that you outlined here should apply to essentially any model, any classification task with a close enough that is close enough in terms of mathematics and domain. Is that right? So it's obviously you got your ideas from image classification. Now you applied it to natural language understanding, but it's probably applicable across the board. Is that right?
Yeah, I mean, as long as you train with a cross entropy loss or some kind of I mean, as long as you can adapt the loss the way we did it. Yeah.
Right. And the second question refers to what the gentleman said. Now, your research is probably spread across the last couple of, I don't know, maybe 1, 2, 3 years or so. I don't know. One of your papers was 2020. So, but I would assume that the entire engine would probably be replaceable with an LLM today.
Maybe.
Right. Yeah. Okay.
Any last questions? No, I think then, let's give our speaker another round of applause. And as always, you can stick around and talk to each other and use the time to connect. We still have some alcohol-free beverages around, so you can have them, and hope to see you next time. Bye. Thank you.